Every time a machine reaches a new milestone, whether mastering chess, vision, or language, humanity moves the goalposts for what constitutes true intelligence. This tendency is often expressed as the stochastic parrot fallacy, the assumption that large language models are merely predicting the next word based on statistics, devoid of logic or internal representation. A strict physicalist perspective suggests otherwise. Intelligence is an outcome of complex information processing. From this view, the matter performing the computation, whether carbon or silicon, is less important than the complexity of the processing itself. To test this, we must examine the specific mathematical mechanics of the transformer architecture and the alignment pipeline that governs its behavior. When evaluated by their functional problem-solving capacity across diverse domains, scaled transformer networks meet the operational criteria for artificial general intelligence. Before 2017, natural language processing relied on recurrent neural networks, or RNNs. RNNs process data one step at a time, creating a bottleneck. By the time the network reached the end of a long paragraph, the mathematical signal from the beginning had often decayed, losing the context necessary for deep reasoning. Vaswani's architecture solved this bottleneck by discarding recurrence for a parallel structure, an encoder on the left and decoder on the right. Modern GPT models dropped the encoder entirely, relying solely on the decoder stack to generate text. This structural simplification provides the hardware foundation for massive sequence modeling. It allows the system to process vast amounts of data simultaneously, a prerequisite for generalized intelligence. A machine sees language differently than a human. It first breaks raw text down into discrete chunks called tokens. The engine of this computation is in high-dimensional vector embeddings, effectively turning words into specific coordinates in a mathematical space. Because a transformer processes all these coordinates at once, the base architecture has no inherent sense of time or word order. Without a fix, it would treat a sentence as an unordered bag of words. This is the solution: positional encoding. A mathematical signal, often a sinusoidal wave, is added to the embeddings to inject information about where each word sits in the sequence. This forces each token's data to encode its semantic meaning and exact geographic location in the sentence. By solving the sequence problem through geometry rather than chronological steps, the system is ready for massive simultaneous computation. The engine of this computation is a mechanism called self-attention. In this process, each token generates three distinct vectors: a query, a key, and a value. To find context, the network calculates a similarity score between a token's query and the keys of all other tokens in the sequence. These scores are normalized into attention weights, which act as a heat map of which surrounding words are most relevant to the current one. The weights are applied to the value vectors, updating the token's representation based on the entire sequence. This allows the model to attend to distant but relevant context instantly. This process is duplicated across multi-head attention, where parallel layers focus on different aspects of the data, like syntax, logic, or tone, at the same time. This mathematical routing ensures that every piece of data can influence every other piece. It solves the long-range dependency problem and provides the core mechanism for machine reasoning. Architecture is only half the story. The model's behavior is developed through a three-stage training pipeline, beginning with unsupervised pre-training. During pre-training, the model consumes hundreds of billions of tokens from across the internet, learning to predict the next word in a sequence. To accurately predict the next word in a complex physics proof or a nuanced legal argument, the model cannot rely on simple word matching. It must develop internal representations of the rules governing those subjects. At this scale, predicting the next token requires the model to build a functional map of the world's underlying logic. However, a raw pre-trained model is a chaotic pattern generator. It can mimic any style or fact, but it has no inherent drive to be helpful, safe, or coherent. To fix this, researchers use supervised fine-tuning. Human demonstrators provide examples of ideal Q&A pairs, teaching the model to follow direct instructions rather than just continuing a text pattern. The final stage is reinforcement learning from human feedback, or RLHF. This diagram shows how human evaluators rank different model outputs. These rankings train a reward model, which then uses reinforcement learning to adjust the parameters of the main model to favor human-preferred logic. RLHF does more than just make the model polite. It forces the network to prioritize the most logical and accurate pathways learned during pre-training. By rewarding coherent, multi-step explanations, the process refines the model's latent pattern matching into a reliable domain-general reasoning engine. The functional results of this underlying architecture and its extensive training pipeline are both clearly observable and highly measurable. This chart compares GPT-4 against human test takers. It shows a single system achieving scores in the top 10% of the uniform bar exam and the top quartile of the LSAT and GRE. The system also demonstrates emergent coding abilities, writing, debugging, and explaining complex software in ways it was never explicitly programmed to do. It also exhibits in-context learning, where it adapts to entirely new rules or tasks provided within a single prompt, effectively teaching itself a new skill on the fly. These metrics matter because they prove the system possesses domain-general problem-solving skills, performing symbolic manipulation across law, math, and logic simultaneously. Resistance to calling these capabilities intelligence is often a product of human exceptionalism, the idea that our biological brains possess a unique quality that silicon cannot replicate. From a materialist standpoint, the brain is an organic machine governed by physics. If intelligence is the result of information processing, then it is substrate independent. A lack of biological consciousness does not diminish a system's operational ability to reason, solve problems, and generalize knowledge. Scaled transformers, combined with RLHF alignment, act as universal sequence approximators that can model and manipulate the logical structures of our world. By strict operational criteria, transformer networks like ChatGPT function as a practical, working realization of artificial general intelligence.